Okay, so welcome everyone to Machine Learning Design Demystified, our participatory session. I hope you're all here ready to participate. So my name's Rick Kaisman. I'm a faculty member at the University of Hawaii and a research scientist at the Software Engineering Institute.
My name is Serge Hazijev. I'm head of Intelligent Enterprise, and this is just an umbrella of several technological services, AI, big data, and IoT.
And my name is Yuri. I'm a data science practice lead for Saucer, where I'm actually leading on our AI, machine learning, and cognitive computing services. My background is primarily technical, scalable machine learning, big data, and deep learning, and today I'll try to introduce you to those exciting things and fields.
So what we've got planned for you for the next hour and a half is, first we'll give you some background, a little bit of context. We will very briefly introduce the game, and you should all have a deck of cards, I think, as the price of admission. We'll talk, once we've walked through a few steps of the game, we'll talk about prototyping, and you'll have a prototyping exercise that you'll be doing one per table. So Yuri will explain the environment that's been set up for you guys to do some prototyping, and then we'll have a summary and Q&A. So to situate this, one of the things that we realized is that teaching design is hard. Learning design is hard. And we came upon this idea of trying to gamify it, create a game that would introduce the concepts of design in maybe a little bit lighter weight way, abstracting away some of the gory details. And so we developed the Smart Decisions game. And at the time, we created a big data version of the game. So the realm of design that we were focusing on was doing design for a big data system. And so those were the components, the technologies, the families that we were interested in choosing design for. But we quickly realized that we could modularize this game, and that the domain for which you were designing could be plugged into the game with no changes at all to the game, and of course with no changes at all to ADD. So you see in the center is machine learning, and today the examples, the cards that you have are for our second instantiation of the game, this machine learning instantiation. So the way we envision design is that design proceeds from, is driven by a set of architectural drivers, and we're just going to give those to you. The design is what we're going to be focusing on, but we're going to briefly mention the later stages after you've designed. What should you document and how should you document it, and then how do you analyze, how do you evaluate the design. Excuse me. So this is the steps of ADD 3.0. I'm not going to go over them, but the steps of the game essentially walks you through the steps of ADD and the design process embodied in ADD. And as I said, you're going to see this instantiated with machine learning design concepts, specifically with problems or categories of problems, with algorithm families, and then with specific algorithms. And your design choices are going to be in each of these three categories. So the game was, it was 3 years ago. The game was first presented 3 years ago at SATURN. We have a website, smartdecisionsgame.com, where you can currently download just the big data version of the game, but hopefully we'll add this at some point in the near future. And we have found that this is an engaging way to introduce people to the idea of design. A game contains the idea of a score, and the score tells you how well you've done. It gives you some immediate feedback, even though it abstracts some of the ideas. So without further ado, I will turn it over to Serge, who will introduce some of the background.
And first, let's start with a short quiz as a part of our gamification activities. So guess what is the name of this company in AI field? And you may see it was flat for many, many years, and just 2 years ago it started growing as crazy. So if you had put 100K, for example, you would have received 1 million today, just a side note. So any clues? Tesla? Well, it's close, but not exactly Tesla. Probably Tesla is a client of this company. Any other ideas? So I would give you a hint that this is a hardware company, and it was in more traditional hardware computer equipment. NVIDIA, yeah, bingo, that's right. So as you may see, this picture is a great illustration, actually, of expectations in AI nowadays, from investors and from consumers. Pardon me? NVIDIA, yeah, NVIDIA. So it was famous for producing video cards, and I will go back for a second. Now it's famous for producing GPUs, GPU units, which are accelerators of complex machine learning computations. So let me give you a little background, just a recap of AI history. AI as a term was coined by John McCarthy in 1950s, and at that time, actually, there was a great hopes for this field, a lot of hypes and so on and so on. But within roughly 4 decades, there was no so visible achievements in this field. So there were two, I would say, showstoppers or blockers, if you will. So one of them was actually lack of computational power, and another was slow advance in AI methods. So at that time, a researcher or a scientist would operate from top-down positions, right? So just, you can consider as a magician creating some kind of formula. Statistical modeling or expert systems, just, illustration of it. And the situation was changed in the 1980s by introducing machine learning. So it revolutionized the field of AI. So instead of top-down approach, nowadays the researcher or machine learning experts is a trainer of that system, is a supervisor. So the system is learned, is training and learns itself from provided data. So that's the major difference right now. And deep learning is considered as a paramount of machine learning techniques right now. So how many of you heard about deep learning? Yeah, so I would say that this is too basic stuff for you, and we can go quicker. So just a brief summary. AI is an umbrella term. Machine learning is a method of AI, and deep learning is a technique of machine learning. And going back into myth and fiction about artificial beings, we can see that there was a fantasy, probably hundreds or thousands of years, about some entities who serve human. Robot, for example, Golem in Bible. And someone believes that Sumerian Anunnakis created the first man, right? And if we are artificial beings, perhaps it explains why we are trying to create some artificial entities who resemble us. And this one is a good illustration and a little bit of speculation, I would say. It's a comparison between biological systems and devices, electronic devices. So you may see here, at that scale, is a number of neurons, and the current advances in AI pretty much close to mouse level, right? So it doesn't mean that we need to wait until AI will reach human performance level. It will be just too late, right, to do some creative stuff. But it's a great illustration that there are still a lot of room in AI advance, and even at this level, we can use machine learning for complex tasks. Complex but specialized tasks, I would say, right? So specialized in analogy, for example, like frog's eyesight is better than human. In the same regard, machine learning system can be better than human in speech recognition or image recognition or even in driving cars. And now, or today, we'll be solving real-life challenges. So this is a banner system, and our goal will be to elevate efficiency of that system, right? To make it better in terms of predicting. So you may see those two silly banners, and end user, actually, who is going to pick banner or click to a banner which fits, better for that personality. So we'll have some features of that user, like demographics, like other characteristics, but we are not going to go, deep into those features. So today we have, too short time to go into extra activities, so that we'll use our training data set as a whole. So no need to, do some feature analysis on that. And this is a architecture diagram so that you can understand better the position of that system. And this is CTR prediction system, actually, right? So CTR is just a relation between number of click-throughs divided by number of impressions. So we are going to improve ratio of CTR using machine learning. And for that exercise, we'll need to choose what will be the best algorithm for our task, right? So we are going to select two algorithms, and we are going to do a rapid prototyping today so that we can select which one is the best using some practical or experiment validation. All right, and now let me turn to Yuri to talk a little bit about machine learning concepts. And please bear with us if you already know those basic principles. Maybe someone will need still, to pick up those fundamentals.
Right. So before getting into the details of machine learning theory and trying actually to solve the problem that Serge just introduced you to, let's think, why do we actually need machine learning here, right? And not only here, but for many other AI-related problems. Why we are all supposed to be good at software engineering, right? Like rock stars. Why can't we just hand code our solution, right? So, and it turns out that it's actually not feasible to hand code many of AI-related solutions. First of all, one of the main reasons for that is that most of those problems, they are poorly defined. So for instance, imagine you want to develop a sentiment analysis system. You want to do some sort of opinion mining against Twitter data and see what kind of, how your customer, what's your customer opinion about your product, right? And there are actually infinite number of ways how to say good or bad things. You can't just hand code every possible rule for good or bad review, right? So you have to somehow deal with this infinite kind of problem space and do some sort of approximation. And another problem is that most of those problems, they are poorly defined, right? So we still don't know how our brain solves those kind of problems. So we can't come up with a well-defined algorithm, and we can't even define what are the typical steps for solving such a problem, right? So that actually kind of motivates us to use machine learning and many other techniques. Yes, nowadays machine learning is kind of a frontier, or deep learning frontier of AI methods, but I think maybe in 10 years we'll have another way to do the same things, but that's actually the main motivation. Why can't we use traditional software engineering? So to put it into more technical analogy, right? So we used to see that developers write code and write our and code our solution. But in machine learning case, there is an algorithm that actually write the code. And instead of code, we have some kind of bunch of matrices and vectors and some weird way how to multiply them. But that's actually the code. It does the same logic that we used to have in Python, R, Java, C++, or whatever we use, right? So, and here are some basic building blocks that are similar for any given machine learning solution. So there is always a machine learning algorithm. And the goal of the machine learning algorithm is to leverage historical data that we have in order to come up with a model, where model is actually, as we just described, it's a code that will be executed on a new data to predict the value on the data that we haven't seen yet, right? And you may also notice that our historical data is divided into two subsets. One is training data, another is testing data. And that actually is a very important trick that we use in machine learning, because our goal is not to memorize the data, right? We want to extract some sort of general knowledge about the problem so that we can apply this knowledge to any kind of data. It's the same nature, right, to new data. So we try to simulate this circumstance, right, by dividing our historical data set into two subsets. That one we use for training, and another one we use only for validating or simulating this real world behavior, right? And that's actually one of the main concepts why actually machine learning works. And although in theory we have kind of huge explanation why it's theoretically feasible, but without this trick we actually can't come up with a model that will perform well in real world scenarios. So now let's try to think what types of learning are there. And in machine learning community, we consider 2 or 3 basic types of learning. And today we're going to discuss only 2 of them. So first one is supervised learning. And the main kind of specific of supervised learning is that in this circumstance, in this setting, we have, for our algorithm, both input and output is available, right? We can leverage both input data that we want to use to predict and the ground truth data that we want to predict in the future. And the goal of the algorithm is to uncover some sort of mapping or general relationships between input and output data. And another example, here is an example of supervised problem. So imagine you have a data set of house kind of sales, right? You have some features for each house. You have square meters, you have location, you have a bunch of different features, right? And you also have some historical data on the price that particular house was sold, right? And what you would like to do is to create a model that will recommend a price for any given house, right? So based on its feature, what would be the kind of recommended price? And you can use it, for instance, you work for Trulia or for Zillow, you want to use for your customers to come up with the best price for their properties, right? And in this example, input data would be house features and output data would be actual price. And the goal of the algorithm or the model in the end would be to predict house prices based on those features. And another kind of setting is unsupervised learning. And the main difference is that in unsupervised learning setting, we don't have any idea about our output, right? We have only input examples, and what we want to do is to discover some sort of internal structure of the data and see whether we can leverage this structure. We can try to motivate our algorithm to go in some direction that we already have some sort of prior knowledge what kind of output we expect to see, right? But we have no idea whether this is kind of the case, and we have to validate it with our data, right? So here is an example. Imagine you have a bunch of customer transactions, and you want to create some sort of customer segmentation model, right? You've no idea how many segments are there. Maybe there are 10 segments, maybe just 2 segments. You don't have this information in advance, but what you have is that you want this segmentation to be done based on a customer similarity. And you have some sort of metric how you define this similarity between different customers, and you actually, that is the way you motivate your algorithm to leverage this information. And in the end, you can try different number of segments, and then you may come up with some best best segmentation scenarios that you will use that will describe your data in the best way. And here is another illustration of the same 2 concepts. So it's actually the same problem, right? So you have on the left you have a plot which kind of represent typical supervised learning case, right? We have some number of observations, and we have already labels associated with each observation. And in another case, the same data, but without output information, without ground truth labels, right? You can still see this kind of similarity, right? You can still see that this particular group maybe belongs to this group of observation belongs to a single group, and another one belongs to another group, and you can still leverage from the structure of the data. So this is kind of the main example, or kind of another way to represent those 2 concepts. And the third type of learning is called reinforcement learning. I would say that nowadays it's the least we don't have real kind of production use cases for reinforcement learning right now. That's why it's not really mature in general. There are a couple of applications in stock markets, in robotics, but still we're still on the way. And the main difference of reinforcement learning is that it's actual interactive way to learn. So you have an algorithm, and you have some sort of objective. For instance, you have an algorithm for a self-driving car. And you kind of motivate you kind of put your algorithm, your device into real life and let it go as it is, right? So try different techniques, try to drive in different ways. But what you do, you kind of set up some sort of objective for your model, for your device, that it should go from A to B. Whatever it takes, whatever action it should take to get there, we do not care. We let our algorithm or our model to discover those ways and find the best way to get from point A to point B. All right, so let's get back to our problem definition, right? So we have our problem with the CTR prediction system that we want to develop. We have our historical data, which consists of logs where we have user features. Those features, once again, could be like device, IP, demographic features. And we have 2 banners that we want to advertise. And we have historical information whether user X clicked on the banner A when it was shown or not. So click or 0 stands for click, and 0 stands for means that there were no click, right? And 1 means that actual user clicked on that banner. So in our case, what do you think? What type of learning we are dealing with, and what type of learning will fit this problem the best? Any clues? Why supervised? Right. I don't know. I've heard this kind of the main kind of word here is label, right? We already have labels in our data set. We already have information whether for this particular user, this particular buyer was interested or not. And why don't we actually leverage this information? If we already have it in our data set, it would be silly just to get rid of it and try to apply unsupervised learning, right? So that's why, in general, this problem can be considered as both supervised and unsupervised, but naturally, supervised learning fits this problem statement the best. So now let's get to our machine learning cards. So now that we know that we are dealing with supervised learning kind of setting, let's try to use our cards to select 2 candidates for our solution. And here is the structure that we have in each deck. In each deck, there are about 4, I think it's 4 cards with a green back. Those cards represent problem types. We have, I think, about 8 cards with a blue back. They represent algorithm families. And algorithm family, in general, it's a group of algorithms that are quite similar in its nature, but I would say that for some cases it's even the same algorithm, but different variations of the same algorithm, right? And the last one is actual algorithm. That's the card that we're going to use for our practical exercise. And we have 3 more iterations, or actually 2, right? We will try to select the best problem type for our challenge. We'll try to select either 1 or 2, I would prefer to use 2 algorithm families and 2 algorithms from those families. And then we'll try to test them and see whether we were right or not with our choice. So here is the structure, once again, 4 problem types, 8 algorithm families, and a bunch of algorithms that belong to each family. So do you have any question? Does it make sense, the structure of those cards? I would recommend you to group them right now based on their kind of type. So group green cards, blue cards, and red cards. It will make everything much easier for you once we get to the actual selection. In the meantime, if you have any questions while we are kind of unpacking our cards and grouping, feel free. All right.
And let's check. Does everyone has cards? Yeah? Super.
All right.
All right.
So let's get to our first iteration where we're going to use our cards. And what we will try to do is to kind of define what kind of problem we are dealing with, right? Machine learning problem. And in machine learning community, we have 4 basic types of problem. They originally come from data mining, which is another field. I'm not going to go into that, but generally speaking, any machine learning problem in some way falls into one of those problem types. So first type of problem is classification. And the goal of the classification algorithm is actually to assign some sort of label to an observation. We know, and the number of those labels, we know in advance, we know that we have 5 different types of customers, or we have either fraudulent or not fraudulent transactions. So we already know what kind of labels we're going to use, and the goal of the algorithm is to, once again, uncover this connection or relationship between our input data and the labels that we want to predict. So another example of such problem might be face detection for images, right? We can go use some sort of window and check whether this particular window contains a face or not. And that still would be a classification problem because there are 2 classes, face or not face, right? The second type of learning is also quite similar to classification, but it deals with quite different output space, right? We call it regression, and the goal of regression is to assign a continuous value to a particular observation. So generally speaking, any kind of float value that we want to assign, it can be demand for a particular product, or it can be a credit score for a loan application, right? So, and I would say that in machine learning community, we quite often say that classification predicts whether some event will happen or not, and regression predicts what will be the influence of that event, right? So they're quite similar, but they deal with different kind of things. And for some use cases, they both can be applied, right? And both of those, both classification and regression, those are examples of supervised learning because we usually already have our kind of output information in advance, and we want to uncover that kind of relationship. Another type of learning is clustering. It's the first example of unsupervised learning problem. And the goal of clustering is actually to uncover those kind of groups of observation and analyze the structure of the data and extract those groups, those observations that are similar or may belong to a single group based on some sort of similarity that we have in our mind. So for instance, we want to discover our audience on social media and see what kind of groups or segments we have in our audience, right? Or for instance, we analyze geodata and we want to see whether our check-ins, our user check-ins, whether they belong to some single location, right? Or they spread across the whole kind of map. Or we want to detect we want to analyze our knowledge base and see what kind of topics are discussed in our knowledge base on Confluence, right? So that would be another example of clustering. And the last one, and I would say the trickiest one, is anomaly detection. It can be both supervised and unsupervised learning problem, but in general, the goal of the anomaly detection model or solution is to first identify what is the expected pattern that we expect from the data or from behavior, and then detect some sort of deviation from that pattern, right? And for instance, the same type of problem that I've just mentioned, detecting fraudulent transaction, can be considered both supervised and supervised. For instance, we already know that there is some sort of typical type of fraud that exists. We already detected it, we faced it, we experienced it many times. We have a lot of training data that we can use to detect this particular type of fraud, right? But those guys, they also evolve, they develop new methods, and we want to know that something bad is going on, even if it's the first time we experience this, right? We want to see that something happens that we didn't expect, right? And in this case, we can apply unsupervised anomaly detection algorithm to detect those kind of things. So if we get back to our problem, right? Here it is, our two banners, our data set with user features and the information whether this particular user clicks on that banner or not. So what do you think? What type of problem will fit this kind of challenge, about this use case? Is it clustering?
So now, I think that now we can use those cards and work in working groups, actually. So you can use one card deck per table and decide together what would be the problem type. Right. So this is our next iteration.
Right. Thanks.
All right.
Problem. Here is the problem. So there's going to be one vote, one card per table. So you have to agree on a particular problem type. It should be easy. We have only 4 options, so.
I already got it. It's a classification problem, so they're already getting it.
Okay.
Yeah.
Cool.
So does anyone need more time? I'm not hearing any objections.
All right. Let's wait another minute.
Yeah, why don't you poll the audience?
We can check, poll the audience.
Okay, so who think that the challenge that we are dealing with is kind of related to anomaly detection? No one. Maybe it's clustering or regression. I think we all agree that this is classification problem, right? Yeah, that was easy, although there was a trick, because our end objective is to optimize for CTR, for click-through rate, right, which is actually continuous value. But what we have here in our machine learning setting, right, we have actually binary classification problem. We have only click or not click, right? So that's why this problem actually can be considered as both classification and regression. But I think that classification is a more natural way to deal with this problem. So I think you all are right in this classification. Now let's try to select our candidates, right? We have our families and algorithms. And if you look at your cards, you will notice that in top right corner, there is a blue circle, which means that this particular algorithm or this particular algorithm family can be applied to the classification problem, right? So there's also red for anomaly detection, green for regression. So, but we're gonna focus on those that have this blue circle in the top right corner. So there are 5 cards, 5 family cards for classification, and there are 9 cards for algorithms. Is it 9? Yeah, it should be 9. So now I'm going to give you 1 minute to kind of shuffle your deck and select those cards, because those are the ones that we're going to use for our practical exercise. Five families and 9 algorithms.
So you should make it clear they don't have to choose anything.
Yeah. So you don't have to choose anything. We just shuffling to make our kind of future algorithm selection much easier. So you don't have to go through the whole deck. We are on time. All right, so now we've got quite a huge bunch of cards, right? And now we have to select only 2 out of those, right? And what kind of motivation we can use to make this decision, right? To make this selection. And it turns out that the main decision drivers, they actually are motivated by our business goals, business drivers, business requirement that we have for our solution. So now let's try to kind of connect our requirements, our business drivers to the actual algorithms and algorithm family. So for instance, for algorithm family, we have 5, 6 main drivers, right? For instance, first one is big data, which means whether a particular algorithm family can be applied to large-scale data sets, right? Whether there is a good implementation of this algorithm available, or whether this algorithm actually designed for big data, because some of them are not, by design, cannot be applied to large-scale data sets. Another driver is small data, which is also quite important, because for some problems we don't have really a lot of data, but we still want to leverage it and kind of be as much efficient as possible to get some sort of knowledge from this data. Third one is imbalanced data, which is actually important for our use case, right? Because it turns out that it's quite easy to develop an algorithm that will be 90% correct. Just assume that none of the users will pick on those matters, right? And actually it will be 90% correct, right? But that is not something that we want to do, right? We want to focus on that part of our data set where we actually have kind of an impression and the user actually clicks. So we have to use either specialized techniques for our algorithms or algorithm that by design can handle this imbalance in the data. And actually, in the real world, actually nothing is perfectly balanced, right? We quite often see that there is some sort of bias to there is some sort of common class or some sort of common value that that we actually don't want it to overfit to, right? And the fourth driver is result interpretation, which is quite important, for instance, in healthcare, right? So it's not enough for a physician to prescribe some sort of a drug just because there was activation above threshold on third level of the neural network, right? There should be some sort of human-friendly interpretation through the result. And for some cases, interpretation itself might be even more important than the result, right? The next driver is online learning, which is quite important these days because some of the algorithms that we have in the machine learning community, they can learn in a continuous way on a continuous kind of data stream. You have to train on the whole data set available, on the whole historical data each time you want to update your model, which might be quite expensive if your data, the scale of your data is terabytes, right? You can't afford retraining your model every day on tens of or hundreds of terabytes of the data. You want to leverage your data as soon as it comes, right? And use those insights and not to retrain your model's whole data set. And the last one is ease of use. And by ease of use, we mean that those algorithms, because some of the algorithms are quite easy to tune, right? It's quite easy to get some initial result, but quite hard to tune, right? Usually because of the number of hyperparameters. For some algorithms, the number of hyperparameters might be even bigger than the actual data that you're dealing with. For instance, for neural networks, right? There might be a couple of minutes of hyperparameters that you have to choose manually, and you deal with a data set like a couple of 100,000 data points, right? So that's a very important point, and here we see that we're going to use this driver for our challenge. So for our challenge, we see that big data and balanced data and ease of use are important, and we don't want to pay attention for other family drivers. And for algorithm itself, we also have 5 drivers. So for instance, accuracy. This is important in any given case, right? We always care about accuracy. So that's why we're going to use this for our challenge as well. Training speed is also important because some of the algorithms, they require a lot of computational power, and especially in this big data era, right, we want to kind of minimize the cost of our solution. Prediction speed is important for real-time prediction. If you want to predict a banner for a user in the real time, we have only 2 banners in our case, right? But in reality, there will be hundreds of thousands of banners and each one they have to score for every particular user, which kind of puts some sort of strict requirement on the actual prediction speed. Overfitting resistance is also quite an important driver for algorithm. It means that whether the particular algorithm is able to extract generalized knowledge, well, all of them are able, whether they're good or bad, right? And this driver is important for us small data sets, but since we are dealing with a quite large data set, it's not important for us in this case. And probabilistic interpretation, it can also be important, for instance, if you want to, if it's not enough for you to know that there will be rain or there won't be rain tomorrow, right? You want to have some sort of probability of rain tomorrow because you want to penalize your risk and so on and so forth, and you want your algorithm to provide you not only a label but also some sort of kind of confidence, right? Whether how confident we are that the rain is going to be tomorrow. So now that we discussed those drivers, let's try to do our kind of candidate selection. So what we have to do right now, we want to select 2 algorithm families based on the 3 drivers that we've just described: is big data and balanced data and ease of use. And out of those 2 algorithm families, we also want to select 2 algorithms based on their accuracy, training, and prediction speed. So I also recommend you to do this exercise in the room, because our practical exercise that will be next, right? We will have to, there will be 1 practical lab for each table. So that's why kind of your selection right now, the algorithm that you select right now will be used for lab in your group. So let's have a 5-minute break to do this algorithm selection.
So you're going to be using the scores on each card labeled with these categories to guide you to make your selection.
Right, that's a good point. So for each algorithm, there is a table with characteristics, and there is number of stars, which means whether this particular algorithm is good or bad. All right, so let's see what we've got. So I think we have quite natural 6 teams here, right? Because we have 6 tables, or even 7, right? We also have a team right over there. So now let's go kind of table by table and see what kind of candidates each kind of team selected. I don't know. Whoever is ready. How about you? Do you have 2 candidates? Yes. So who's your candidate?
We have multi-layer perceptrons and random forest.
That's a good choice. You guys? Are you ready with your candidates?
Sure. You want the family and the algorithm?
No, just 2 algorithms.
Just the algorithm?
Yeah.
Why did it speak for everyone here? We have random forest and classification of rational trees.
Okay. They're quite similar in their nature, right?
Okay.
So
A different one would be linear regression.
linear regression can be applied to classification. Linear regression can be, there should be logistic, right, yeah. I would recommend to choose logistic regression just to see kind of different, just to select really different types of algorithms, because regression trees and random forests, they are really similar in their nature. All right, next table, what are your choice? The choices. Random forest and okay, do you have any backup options instead of cart, instead of classification regression trees? Okay, let's do logistic regression. Next table, you guys.
We had logical regression in random forest.
Okay, the next table here, second table, or
Generalized linear and also the decision tree.
okay, and the last, no, not the last, sorry, the next, you guys.
We have decision tree and random forest.
All right, and the very last group, but not the least.
Well, we said classification regression trees and multi-layer perceptrons.
Oh, that's a good choice.
And we did one was random forest and multi-layer perceptron.
Okay.
All right.
Okay, so we have at least 3 different kind of pairs. So yeah, and you know, it's not enough just to do this exercise, right? We have to validate our results, right? Because the goal of this exercise was just to narrow down the scope, because trying or checking or validating every kind of algorithm would be, I think, first of all, inefficient, and for some cases, it's not really feasible to check all possible algorithms. We just selected the candidates that we're gonna check against our real data, right? So, which is going to be our next step, but before getting into that, we have some insights from Serge.
Yeah. All right. So you made early decisions, actually, and that was a result of architectural design step in this process. And the next logical step, of course, is to document your architecture, right? For this purpose, we use Jupyter Notebook, and we are going to use it today. So Yuri will provide just in a couple of minutes the links to connect. All of those notebooks, they online, they are hosted, and you just need browser, that's it. And talking about architectural evaluation, or rapid prototyping we call it, in this regard, we are going to use several tools. So one of them is, of course, Jupyter Notebook. Another one is a library. It's a Python library, scikit-learn. And that actually is a pretty common tool set for data scientists. And for architects, it's quite important to understand what tools are available and also be a part of that process. So let's take some time for prototyping and evaluating our algorithms. But before that, I would like just to highlight that for prototyping, we have a pretty good method, if you will, defined. So this diagram actually shows when and what prototype to choose, right? So there is a variety of prototypes, starting from proof of concept and continuing with minimum viable product, for example, or horizontal prototype. So today we will be doing proof of concept. All right, yeah, so let's switch to prototyping.
Yeah, so what we did, we prepared for you 10 different environments for rapid prototyping. So there is one URL per each group. So since we have 7 groups, please use URLs from 1 to 7, and there is a password. So let me go with you. So imagine I'm in group number 10.
So where will we start our counting?
Yeah, 2, 3. Right. So imagine I'm in Teams 8. I go to this URL, and once I get there, there is a bunch of files, and you have to open this SATURN ML game scenario file, which is actually consists of some kind of refresh information about our use case. And by the way, how many of you are familiar with the Jupyter environment? Just raise your hand. So we definitely need some introduction. So what is Jupyter? It's an interactive environment originally for Python, but now it's available for many other languages. The basic structure is that we have different cells here. We have cells that contain the actual code that can be executed in an interactive way. And we also have some textual cells, which is actually represents some sort of kind of textual or visual information.
So this is an example of documentation, actually. And here, documentation and code is in one place.
Right. Right. In the end, you can easily share these results with your colleagues. So along with the code, it's actually great in data science community because it really helps to collaborate in a more efficient way. So you can select each of these cells and press run. And if it's a code in this cell, you will see the result right above. So let's wait. Still loading. So this asterisk means that this cell is running right now. And once it finishes, let's wait. It's wrong. If you see any problem, there is a way to oh yeah, it's finished. So once it's finished, it either outputs the output or it just marks it that it's done and kind of in the order that each cell was run. So for instance, for this cell, which actually tries to load our training data set, once it gets loaded, it outputs some sort of first 5 rows from the data set that we have here. So what you have to do for this lab exercise is to run each cell one by one. So first start with this one, then load data set. You see what is the structure of our data set. Then do some kind of data preparation. For instance, here you can see distribution between clicks and non-clicks. And that is kind of what I mentioned before, that our data set is kind of skewed, right, or biased. And we want our algorithm to focus on this right group and don't want to predict that any given banner won't be clicked. So there is no input is needed for these cells. Then you have to prepare your data set and see how your kind of transformed data set will look like. Then finally do some feature engineering to reduce the kind of feature space, because here we have about 10,000, right, 11,000 features for our data set, and we want to reduce it to just 50 features, and there are some techniques which help with this dimensionality reduction. Then you prepare your training and test data set and see that there are 8,000 observations or examples in training data set and 2,000 in testing. And here is the only field where we will need your input. So here what you have to do is to put the algorithm that you selected on the previous stage and add them to this list. You can just pick any of these kind of algorithms that you have here and just paste them into this. So let's try. For instance, I selected this one and something else, maybe no one selected key neighbors, like this. Let's go. Then you should continue running each cell one by one. Once you finish this training phase, you will see some initial results that you have. You will see training accuracy and test accuracy, training time and prediction time. And then once you get this idea of what would be the performance of this algorithm that you selected kind of out of the box, right? You can try to deal with the different hyperparameters that are available for each particular algorithm, if there are any, right? Because for instance, for Bayesian naive classifier, there are no hyperparameters. So what you get on this initial stage will be your final accuracy. But for some of them, for instance, for multi-layer perceptron or for neural network, there are quite a lot of them, and this is just a small subset that we prepared for you. So you have to keep running each cell one by one. The next step, we'll try to tune or do actually some sort of grid search over these hyperparameters and try to find the best set of hyperparameters for your algorithms using actually the same algorithms that you selected for training. So this is the list of the algorithms that will be used for both training and for testing and tuning. And in the end, you will have your final result. You will have train accuracy after tuning, test accuracy after tuning. You will have tuning time for your algorithm and training time for a single algorithm to train on a subset of data and prediction time. So now let's try to evaluate your results.
So let's get back to IP addresses.
Yeah, I forgot. Here are the. So we have 7 groups.
One laptop per group, so these sessions cannot be shared. So just choose one person in each group to be the driver.
All right, so I think you all got some sort of impression and try to validate your selection, right? And ideally, right, you can try more, you can do a bit more with this. You can try to do more complex feature selection. You can try to do kind of broader hyperparameter search and so on and so forth. And that is actually what we already done for you, because in this lab you used only a subset of your data. We trained all those algorithms on the whole data set, and I'd like to share with you the results. Where they are? Here they are. So here is the result that we got from training on the whole data set. So I think all of you selected random forest as at least one of the candidates, and you see that this is a winner kind of even once we train on the whole data set. The second one, surprisingly, is k-nearest neighbors, which is actually not an algorithm itself. It's rather a storage or database that you can query and select the most similar examples. But it turns out that the performance of this algorithm is quite good. But you can see that prediction time, since the kind of database is quite huge, it's really large, so this algorithm can be applied for real-time circumstances. And the next one is logistic regression, which I would say is the second winner in this competition. And for instance, there is another interesting insight. Take a look at multi-layer perceptron or neural network. You can see that the initial result with default hyperparameters, it's quite bad, right? I think it's worse out of yeah, it's right than it's reward. But once you apply some sort of tuning and try try to deal with this, play with this algorithm, the performance is much better, right? And this is the case almost always with multi-layer classical or deep neural networks. You have to spend a lot of time on actually tuning and selecting those hyperparameters, and there is a huge room for that improvement.
One quick question.
Sure.
When you say initial accuracy and final accuracy, is it the accuracy for the data that we have, or how does it? Because we have a data set, and is the accuracy based on the rows in the same data set as well?
Yeah, it's the same data set, but using different set of hyperparameters. So initial means that we use default hyperparameters, and tune means that we try to do this grid search. And another important insight is SVM, because SVM used to be quite famous algorithm, especially in the 90s, because it's naturally designed for small data sets. And since we didn't have a lot of data back in the 90s, SVM was one of the most popular algorithms. But as you can see, once we get into this big data era, you see that actual performance of this algorithm is not the best. It's on the same range, but still not the best. But training time is really huge, and the problem is in the actual design of this algorithm. It doesn't really scale. The complexity of this algorithm is exponential. That's why it's no longer a good choice for nowadays challenges and nowadays problems. And naive bias classifier, it used to be quite famous algorithm, and it's still applied quite often to tasks like spam detection, but for many use cases, we don't even consider naive bias as a candidate. Yeah, so now let's switch to some takeaways.
Yeah, all right. Thank you, Yuri. All right. So, just key takeaways of this session. As you see in machine learning, solution design actually is an iterative process, right? Like in the same way as you design, for example, a big data system or IoT system, you do some iterations in order to make decisions. And here, actually, what we see in that ADD principles help make machine learning design in a systematic way. So it means that we can leverage the architectural practices. We can leverage foundation of architecture which was developed for decades in machine learning, which is booming nowadays. And the machine learning cards itself, they aim to select candidate algorithms, to do some kind of top-down design decisions, and reduce of variety of alternatives, right, to narrow down your decision tree. And as you noticed, prototyping is a necessary activity so that you can see what is the best winner from your candidate algorithms. So that's why we suggest that you pick 3 or even more algorithms, but 2 or 3 is a good number as an initial step, as a design process activity, and then use some experimental methods like rapid prototyping in Jupyter Notebook for selecting the best algorithm for your task. All right, so thank you very much.